I am AKB Anjan Kumar Bhuiya from the Department of Mathematics, Vishwabharati. Today we start chapter 7 of this course. This is on the factorizations in integral domains. You all know the name integral domain comes from the term integer, and integral domain is generalization of the ring of all integers. Till now we have learnt a lot on the integral domains, but no discussion on the major properties of the ring of integers like division algorithm, like prime numbers, or nothing on the fundamental theorem of arithmetic, which states that every integer greater than 1 can be expressed uniquely as a product of prime numbers. In general, on an integral domain, there is no analog of the division algorithm. In this chapter, we will characterize the integral domains such that there we can get some analog of the division algorithm. We have elements like prime integers and integral domains such that we get unique factorization. In the first module, we discuss divisions in commutative rings. Let R be a commutative ring with 1 and AB be two elements of R. Also assume that A is non-zero. Then A is said to divide B if we have an element C in R such that B is a multiple of A, that is B equal to AC. Also we say that A is a divisor of B and it is denoted by this symbol. Henceforth, when we write A divides B, we mean that A is non-zero, and the notion A does not divide B will mean that A does not divide B, that is B is not a multiple of A. This notion of divisibility give rise to a binary relation rho as follows. See that since R contains 1, so rho is reflexive, and also because of commutativity rho is transitive, but rho fails to be symmetric. For example, consider R equal to Z and two integers 2 and -2. Then both 2 divides -2 and -2 divides 2, still they are not equal. Now in Z we see that M divides N and N divides M if and only if M is equal to either N or minus N. And if F is a field, then in the polynomial ring Fx, given two polynomials Fx and Gx, if Fx divides Gx and Gx divides Fx, then we have Fx is equal to some constant multiple of Gx, and since F is a field, this constant A is a unit. Thus, we see that in Z or in Fx, two elements A B if divides each other, then either B is a unit multiple of A or A is a unit multiple of B. From this we have the notion of associate. In a commutative ring with two non-zero elements A and B are said to be associate of each other if either of them is a unit multiple of the other. In Z, we know that 1 and minus 1 are the only units, and hence if A is a non-zero integer, then A has only two associates, namely A and minus A. Here I would like to clear one thing. This chapter is designed to generalize major properties of Z. Then there is an important question: why should we generalize these properties? If there is no examples of integral domains other than Z or the polynomial ring f x over field F, which has such generalized properties, then we think this is meaningless. So, here besides examples on Z, we will give different other examples of integral domains where such generalizations holds. Such an example is the ring Z I root 5. This is the set of all elements of the form A plus I B root 5, where A B are two integers. Now, we show that this ring has only two units, 1 and minus 1. For this, consider A plus B root 5. If A plus I B root 5 is a unit, then we have another element C plus I D root 5 such that their product is 1, and from which we also have A minus I B root 5 into C minus I D root 5 is also 1. Taking their product, we get A square plus 5 B square into C square plus 5 D square to be 1, and which again implies that A square plus 5 B square must be 1, and it has only two possible solutions. One is A equal to 1 and B equal to 0, the other is A equal to minus 1 and B equal to 0, and these two solutions gives us 1 and minus 1 are the only units in Z I root 5. Thus, every non-zero element A plus I B root 5 in Z I root 5 has two associates. One is A plus I B root 5 and the other is minus A minus I B root 5. Now, we show that if A B are associates, then A B generates same ideal, that is, the ideals generated by A and generated by B are the same. Here we show that these three given conditions are equivalent. First, we prove 1 implies 2. For this, assume that A B are two associates. Then we have some unit u in R such that A equal to Bu. Since u is a unit, it has the multiplicative inverse which we denote by u inverse, and then A equal to Bu implies that B equal to Au inverse. Thus, from A equal to Bu and B equal to Au inverse, we get A divides B as well as B divides A. Now, we prove the condition 2 implies the condition 3. For this, let B divides A. Then we have A equal to BC for some element C in R. And since A is a multiple of B, so A belongs to the ideal generated by B, and it follows that the ideal generated by A is a subset of ideal generated by B. Similarly, A divides B implies that ideal generated by B is a subset of ideal generated by A. Thus, we get ideal generated by A and the ideal generated by B are the same. Now, we prove that the condition 3 implies that the condition 1. Assume that A and B are two elements of the ring R such that they generate the same ideal. Since A belongs to the ideal generated by A, so A belongs to the ideal generated by B, and hence A becomes a multiple of B. Assume that A equal to BQ1, and similarly we have some Q2 in R such that B equal to AQ2. These two together imply that B equal to BQ1 Q2, which again implies that 1 equal to Q1 and Q2. Since the ring R is an integral domain, we can apply the cancellation law, and which implies that 1 equal to Q1 into Q2. Thus, Q1 and Q2 are units, and from the relation A equal to BQ1 and B equal to AQ2, we conclude that A and B are associates. The notion of greatest common divisors of two non-zero integers is an immediate consequence of divisibility. If m and n are two non-zero integers, then a non-zero integer d is said to be the greatest common divisor of m and n if d is a common divisor, and this is the greatest among all common divisors, which has an equivalent characterization that d is a common divisor and all other common divisors divides d as well as d is positive. Now, in a commutative ring with 1, we introduce the notion of GCD, but there our main problem is that there is no notion of order. So, we cannot say greatest among all common divisors. That is why we will use as definition the equivalent characterization of the greatest common divisor of two integers. So, if A and B are two elements of R, at least one of which is non-zero, then a non-zero element D in R is defined to be a greatest common divisor of A and B if D is a common divisor of A and B, and for every common divisor C in R of A and B implies C divides D. Similarly, we define greatest common divisor of any n elements A1, A2, An if not all 0, and we denote this GCD by GCD of A1, A2, An. The most important fact here is to note that we get unique GCD in Z by requiring that GCD is positive, and we get unique GCD in Fx with the assumption that GCD is monic. But in an arbitrary commutative ring with 1, there is no notion of positiveness. At the same time, since in general an element of a commutative ring with 1 may not be a polynomial, so no question of being monic. So, how can we impose uniqueness of a GCD of A and B? In fact, here we show that on an arbitrary commutative ring with 1, it may be that GCD of 2 elements is not unique. For this, consider the ring Z10, that is the ring of all integers modulo 10. Here we show that 2 non-zero elements, box 4 and box 6, has more than one GCD. We show that in fact both 4 and 6 are GCD of 4 and 6. For this, first note that in Z10, 4 is equal to product of 4 and 6, which shows that 6 divides 4. Also we have 6 divides 6. Thus, 6 is a common divisor of 4 and 6. Also, if C is a common divisor of 4 and 6, since it is a divisor of 6, 6 becomes GCD of 4 and 6. Again, 6 is equal to 4 into 4, which implies that 4 is a divisor of 6. Also we have 4 is a divisor of 4, from which it follows that 4 is also a GCD of 4 and 6. Thus, we see that though in Z and in the polynomial ring Fx, where F is a field, we get GCD unique, but on a general commutative ring with 1, there may have more than one GCD. Thus, we see that in an arbitrary commutative ring R with 1, given 2 non-zero elements A and B, there may have more than one GCD of A and B. Now, we discuss the question of existence of a GCD of A and B. In our school days, we computed GCD of given 2 integers m and n without questioning existence. But now we prove that really given 2 non-zero integers m and n, we always have a positive integer d, which is GCD of m and n. This is because of the fact that every ideal of Z is a principal ideal, which we prove formally. A commutative ring R with 1 is defined to be a principal ideal ring if every ideal of R is generated by some single element. For example, Z is a principal ideal ring. Here we show that in a principal ideal ring R, any 2 non-zero elements A, B always have a GCD, and if D is a GCD of A, B, then there exist 2 elements S, T in R such that D can be expressed as SA plus TB. Consider the ideal generated by A and B. Since every ideal of R is a principal ideal, so there is some C in R such that ideal generated by AB can also be generated by C. Here we show that this C is a GCD of AB. Note that since at least one of A and B is non-zero, so C is also non-zero. And since both A and B belong to the ideal generated by C, it follows that C divides A and C divides B. So, C becomes a common divisor of A and B. Now, we show that any other common divisor C dash of AB also divides C, and thus it will be proved that C is a GCD of AB. For this, consider a common divisor C dash of A and B. Then we have some UV in R such that A equal to C dash U and B equal to C dash V. Now, C belongs to the ideal generated by AB implies that C is equal to SA plus TB for some ST in R. If we replace A by C dash U and B by C dash V, then we get C is a multiple of C dash, that is C dash divides C. Thus, C is a GCD of AB. Suppose that D is a GCD of AB, then both D divides C and C divides D, which implies that ideal generated by D is equal to ideal generated by C, and which is equal to ideal generated by AB, and hence D belongs to the ideal generated by AB, and so D is of the form SA plus TB for some S and T in R. Now, we introduce the notion of being relatively prime. Suppose A and B be two non-zero elements of R. If one is a GCD of AB, then note that any other GCD U divides 1, and hence U becomes a unit. Thus, it follows that 1 is a GCD of AB if and only if all other GCD of AB is a unit, and not only that, in this case every unit will be a GCD of AB. Thus, here the definition of being relatively prime will be of this form. Suppose A is a commutative ring with 1 and AB belongs to R be two non-zero elements, then A and B are called relatively prime if some unit is a GCD AB. Again note that if a unit is a GCD of AB, then every unit is a GCD of AB and 1 is also a GCD of AB. Here we have the following necessary and sufficient condition for A and B to be relatively prime. If A and B are two elements of a principal ideal ring R, then they are relatively prime if and only if there exists ST in R such that 1 equal to SA plus TB. First, assume that the elements A and B are relatively prime, then we can say that 1 is a GCD of AB, and hence we have S T in R such that 1 can be expressed as SA plus TB. Now, for the converse, assume that we have some S and T in R such that 1 is equal to SA plus TB. We show that every other GCD of AB is a unit. For this, consider a GCD D of A and B, then D divides A and D divides B, which implies that D divides SA plus TB, and so D divides 1, which is equivalent to the fact that D is a unit in R, and hence it follows from the definition that A and B are relatively prime. Now, we give an example of two relatively prime elements. Again, I would like to recall that we can give easily an example of two elements which are relatively prime in Z. Say for example, if we consider 4 and 5, these two are relatively prime because it can be proved that their GCD are nothing but 1 and minus 1 if we consider Z as a commutative ring with 1. But since here our motivation is to discuss also other examples than Z and Fx, so again I consider the ring Z I root 5 and two elements as 2 and 1 plus I root 5. We show that GCD of 2 and 1 plus I root 5 is a unit. For this, recall that in the ring Z I root 5 there are only two units, 1 and minus 1. Now, assume that A plus I b root 5 is a GCD of 2, 1 plus I root 5. Then A plus I b root 5 divides 2, that is 2 equal to A plus I b root 5 into C plus I d root 5 for some C plus I d root 5 in Z I root 5. Similarly, as before, it follows that A square plus 5b square into C square plus 5d square equal to 2 into 2, that is 4. Since both A square plus 5b square and C square plus 5d square are positive, so the possible values of A square plus 5b square and C square plus 5d square are as follows. But the equation 0.1 has no solution in Z, and from equations 0.2 and 0.3 it follows that A plus I b root 5 is either plus minus 1 or plus minus 2. Since 2 does not divide 1 plus I root 5, so A plus I b root 5 must be either plus 1 or minus 1. Hence, 2 plus 1 plus I root 5 are relatively prime in Z I root 5.
Roll.
As the end note of this module, I again repeat that GCD of two elements in a commutative ring with 1 in general is not unique. Actually, if C, D are GCD of two elements A and B, then C, D are associate of each other, and if D is a GCD of AB and C is an associate of D, then C is also a GCD of AB. So, you must be aware of the fact that in the particular ring of integers z and the polynomial ring over a field, there we get unique GCD with the help of the extra conditions that in Z GCD is positive and in Fx GCD is monic, but in a general commutative ring with 2 non-zero elements A B may have several GCD.